Okay, hello everyone. Okay, yes, good morning. And okay, it's Wednesday and there was an add and drop period and there might be some new students in this class. So there won't be no penalty for the past 2 days. So if you change the class, okay, and if you newly registered for the calculus class, then if this is your first day, then you don't have to worry about the penalties for the past two classes. Okay, so but starting today, we will check the attendance and okay, we will check the attendance every day starting today. And for the attendance checking, you need to the join our class through the LMS website. You need to log into mylms.korea.ace.kr and then you need to click the weekly learning and click today's class link. Okay, and then you need to initiate the start the video meeting button to get the attendance checking. And if you have any question regarding the attendance, please email me. Okay. And okay, so we considered chapter one to review some basic definition of a function. And then in section two, we are considering the limits of a function. And we considered some simple situation the other day on Monday. And today we will consider the infinite limits in section two. Okay, so let me open the note and then start today's class. Okay, so we will consider infinite limits today. So the suppose that we have a function f. Okay, and let me turn off my video. Okay, suppose that we have a function f defined on some interval. Okay, centered at a. So we have some interval containing this point a, and our function is defined on this interval. Okay, and actually this function may not be defined at this point a itself, but suppose that suppose that this function is defined at all other points in certain interval containing a. Okay, so your function may not be defined at this. So let me redraw this. So we consider some interval containing a, and we assume that my function is defined on this interval, possibly without, I mean, except at this point a. This function may be defined there, but it doesn't matter even if this function is not defined at point a. Now, if if the values of f in that interval can be made arbitrarily large as this x approaches a. I mean, if you can make, okay, the values of f of x, okay, arbitrarily large by taking x sufficiently close a, then we say the limit of f of x is infinite. Okay, so in other words, what is the opposite situation? If this limit of f of x is not if this is not does not go to infinite, that means my function is bounded. And when I say a function is bounded, then that means there exists a certain number such that the value of this f of x in absolute value cannot be greater than this value m for all x in that interval we considered above. In that case, we say the function is bounded. If such m can be found, then we say this function is bounded. Okay? But in this definition, we have the opposite situation. The value, so there is no such m, and the values of f can be made arbitrarily large, okay, by taking x sufficiently close to a. In that case, we say the limit of f of x as x approaches a is infinite. So that means the function value can be large as we want. Okay? And in that case, we use this notation. And sometimes instead of that notation, we may use this expression to describe the same infinite limit. And as we consider it in the for the finite situation, when we consider the limit, we does not consider the case when x is exactly a. So we just consider some neighborhood of a. So we just consider some neighborhood values of a, but we do not consider the value of a itself. So please be careful. So so the limit of f of x is infinity. That means f of x can be as large as we want. In other words, it can become an infinite as x approaches a. And then we use this notation. So if consider some graph. So here is one example. So the function, so we consider any interval some interval. Then in this interval, the value of the graph just increases without any bound, okay, in both sides of a. The function value, this function is not defined at a in this figure, okay, but if we consider any neighborhood of a, then the corresponding function values will be very large. And this function value can be as large as we want by taking some value near a. And in that case, we say the limit of f of x as x approaches a is infinite. Now, excuse me. At this point, you see this red vertical line. So the graphs of f of x from the left hand side and right hand side are approaching that value, but the graph of the function, this blue curve, does not hit this red one. They don't have any intersection, but the graphs of f of x are approaching this red vertical line, and this red vertical line will be called the vertical asymptote of this graph. And in a similar way, sometimes the function value can be decreased without any bound. Okay, so the function value can decrease without any bound. Okay, on both sides of a. So at this point in this figure 11, the function is not defined at a. Okay, but the values of f are decreasing without any bound. So in that case, we say the limit of f of x is negative infinity. And even when this function is defined, say with a certain value, it doesn't matter. We do not consider the value of f at a when we consider the limit. If I just look at this limit of certain function, we are just looking at the trend of the function near a. So this limit will observe certain trend of f of x near a. Okay, not at a. So we just want to observe a certain tendency, okay, certain trend of f of x. So if the values of f are decreasing without bound, okay, then we say the limit of f of x is negative infinity. And as I said, this red vertical line will be called a vertical asymptote. Okay. So as an example, if I consider 1 over negative 1 over x squared the function whose graph decreases without bound as x approaches 0, then this function, the values of the function will can be arbitrarily large negative as x approaches 0. So in that case, the limit of 1 or negative 1 over x squared will be negative infinity. And in a similar way, we can consider the one-sided limit. I mean, as x approaches a from the left, the values of the function f may increase without bound or decrease without bound. Okay. So in that case, we do not care about the trend for x values, I mean, to the right of a. We just consider the x values to the left of a for this left and the left hand limit. So, for example, if I consider just 1 over x function, as we know, the graph of the function will be something like this. Of course, they do not have any intersection. Okay. So in that case, when I look at this pattern, the trend of the graph, okay, to the left of 0, the values of the function decreases without any bound. Okay. So in that case, so we can say, you may say the limit of f of x as x approaches 0 from the left, that will be negative infinity. But on the to the right of 0, the values of f just increases without bound. So in that case, we say the limit of f of x as x approaches 0 from the right, the values increase, okay, infinite, the without bound. That means the limit is plus infinity. And in this case, the two one-sided limits are different. So you cannot say the limit of f of x as x approaches 0 is infinity. Such expression is not allowed in this case because the left-hand limit and the right-hand limit are distinct. So here are some examples. So in A, when I look at the pattern, the trend of the function to the left of A, the function values are increasing without any bound. And in B, to the right of A, the function values are increasing without bound. So in these A and B cases, the limits are infinity, but in case of A, the left hand limit is infinite, and in case of B, the right hand limit is infinity. And in C and D, you have similar situation with negative infinity. But anyway, the point is when I consider this one-sided limit, I do not I just observe the pattern in just one side. Okay, one side. One side of what? One side of this red vertical line. This, as I said, these red vertical lines are called vertical asymptote. These are called vertical asymptotes. They do not intersect with the graphs of the function. Okay, the graphs of the function are approaching, okay, these vertical lines, and these vertical lines are called vertical asymptotes. So those are the expressions and some, yeah, in infinite limits, and probably you learn this in other courses as well. So let me just go to the next one. Okay, now let us review the properties of f of x. Suppose that x approaches a, the limit of f of x and limit of g of x both exist. In that case, limit of f plus g can be always defined, and this limit is the sum of these two limit values. In other words, given two operations, the limit and addition, okay, you can perform the summation first, and then you can perform the limit operation, or you can perform limit operations first, and then you can consider the summation later. Okay, in either way you get the same results. In number two, we have similar result for the subtraction. Given two functions f and g, f minus g has the limit, and that is the same as the difference between these two limits. In other words, between limit and subtraction operations, you may consider the subtraction first, and then you can consider the limit, or you can consider the limits first, and then you can perform the subtraction. When you multiply a number, any real number, to a function, you can multiply this number and then you can consider the limit, or you can consider the limit first and then you can multiply the number, and then I can extend this number three result to any two functions. Given two functions, you can multiply these two functions first and then you can consider its limit, or you can consider the limits of these two functions and then you can consider their product. And in a similar way, given two functions, limit of f over g will be limit of f over limit of g. Of course, in that case, this limit of g of x must be non-zero valued. So these are some properties. So in other words, simply speaking, between the limit and any arithmetic operation between two functions, you can perform arithmetic operations first and then you can consider the limits. Or you can consider the limits for two functions f and g, and then you can consider this arithmetic operation, okay? Whatever the operation is. So you can interchange the order of these operations and the result will be the same. So that is the first five laws of the limit laws. I just considered this. And then the next one is the power law. So that means given this f, if you consider any power of this function, you can consider this power operation and then you can consider the limit. Or you can consider the limit of the function and then you may perform this power operation. Okay, so nth power of this limit of f of x will be the same as the limit of nth power of f. In this slide, we say the author says this n is a positive integer, but As we know, this power law holds for any real number. So for any real number n, this power law holds. So as a special case, when this n is the reciprocal of a certain number, we get number 7. Say, so we have n is, say, 1 over k, then fx to the 1 over k, and then if you consider the limit, that will be the same as 1 over kth power of the limit of f of x. As you know, the 1 over kth power is just nth square root. Of course, depending on the values of k, okay, the limit of f of x must, so this, the 1 over kth 1 over kth power of limit of f of x is well defined. If it can be defined, okay? So as long as this limit of f of x to the 1 over kth is well defined, in that case, so for example, if k is 2, then limit of x must be positive, right? Like this, okay? So we have this special result from the power law, and if you have a constant function, then limit won't change the value of that constant function. If I have a linear function, say x, then limit of x as x approaches a will be definitely a. Now, if I combine this result with power law, then we can derive the following. So if I consider any power of x, then its limit will be a to the n. And a special case of the power law is this: when n is, as we observed, the 1 over k case. In that case, we have this special case of law the 9. So, but that is trivial. Now, okay, so if I have any power of x, and as I said, this n can be any real number. And if I have x to the n, the limit of x to the n as x approaches a will be a to the n, right? Then if I combine this number 10 with number 3, okay, number 3, then what do I get? Then when I have c times x to the n, then its limit will be, as x approaches a, will be c times a to the n. Now, if I combine this with a sum rule, then that means if I have, say, c1x plus c2x squared, and then if I let x approach a, then c1x will approach c1a, and c2x squared will approach c2a squared, and then their summation will approach the sum of these limit values. So I can combine this. Then this can be extended a little bit further, and if I have any polynomial in x, and then if I let x approaches a, then you get the value of the polynomial evaluated at a, right? So that's what we can derive from the combination of these formula, right? And then, okay, if that's the case, then if I combine this result in this example with the quotient rule, what does that mean? The quotient rule says if I have two functions f of x and gx, and then if I consider the limit of this quotient will be the limit of f of x over limit of gx. And the example I considered was this: given any polynomial in x, and then if I let x approaches a, then the value of the polynomial at a. So if I combine these two facts, then given any rational function which is defined by a polynomial divided by another polynomial. And then if I let x approach a, then the limited value will be the value of this rational function at a. Of course, that the denominator, the polynomial in the denominator cannot have the value 0 at a. Otherwise, the quotient rule does not hold, right? So this, this, these two can be derived easily from the formula, from the previous properties. So, so this is what I meant moments ago. If this function f is a polynomial or any rational function, and if a is in the domain of f, then limit of f of x will, as x approaches a, will be just the value of a, the value of f at a. So this is just one nice and simplifying property of a polynomial or rational function. Okay. I will talk about this part in a moment in some different slide. But the point is that if I have a polynomial or rational function, and if I consider the limit, then you can just evaluate that function at a given point. So as an example, if I have f of x defined by x squared minus 3x plus 2, then the limit of f of x as x approaches 1 will be, you can use the definition of the limit to evaluate this limit, or you can just plug in the value 1 to this polynomial. So 1 squared minus 3 times 1 plus 2, which is 0. So that will be the limit of this function. If I consider a rational function g defined by x squared minus 1 over x cubed plus 1, then limit of gx as x approaches, say, 0 will be just the same as, you can use the properties of the limit to find the limit of this function, but from this direct substitution property above, you can just evaluate this rational function at 0. Then in the numerator you get 0 squared minus 1, and then in the denominator you get 0 cubed plus 1, so you get negative 1, and that will be the limited value of this g function, right? So if the function is a polynomial or rational function, then we can simply identify the limit of the function. Oops. Okay. And if 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 two functions are the if these two functions have the same values at all points in their domain, except possibly, okay, except at A, okay, and possibly, yeah. So if these two functions f and g have the same values at all points except at A, possibly except at A, in that case, the limit of f of x as x approaches A will be the same as the limit of gx as x approaches A, as long as these two limits exist. And this is a simple fact, right? And and when I consider the one-sided limits, I mentioned that we can consider one-sided. I already mentioned this one. So if two side, okay, if two-side limits exist, then that means these two one-side limits will have the same value. In other words, they are equal, and vice versa. If two one-sided limits are, I mean, if they exist and if they are equal, then two-sided limit will exist. So this exists if and only if these two one-sided limits exist and they are equal. In that case, two-sided limits exist. And in some books they use this as a definition, but anyway, this is one theorem we want to use sometimes. And this is probably the most one of the most important theorems in chapter 2. So suppose that I have two functions f of x and gx which are defined near A. Okay. And one of these two functions may not be defined at A. So we do not consider the existence of these values at A. So except possibly at A means these two functions may not be defined at A. They may be defined, but we do not care about the existence of these two values. So as long as these functions are defined near A, and so near A means given this A, we can consider certain interval, some interval. Okay, so f so when x is near A, that means on some on some interval containing A. Okay, so on that on certain interval, gx is always greater than or equal to f of x. Okay, in that case, so if you can find such interval, then this inequality will still hold even when you take the limit. Okay, so if f of x is smaller than gx on some interval containing A, then limit of f of x will be smaller than or equal to limit of gx as x approaches A. The point is the inclusion of this equality here in conclusion. F of x may be strictly smaller than gx even when f of x is strictly smaller than gx. If you take the limit, you must allow the equality. So limit of f of x will be less than or equal to limit of gx, even when f of x is strictly less than gx. Okay? So that's, you need to be careful. So that is one simple theorem. So let me show you the graph. So if, for example, the f of x is smaller than gx, gx in some interval containing a, okay, as in figure 7. In that case, limit of, so f of x is smaller than or equal to g of x on this interval, then the claim is, the conclusion of the theorem is that limit of f of x will be still bounded by the limit of gx as x approaches a. Okay? So that is the claim of the theorem. Now the squeegee theorem, or sometimes it is called the sandwich theorem, the squeegee theorem says if I have three functions, f of x, g of x, and h of x, and if there is a some interval containing a, okay, and on that interval, f of x is less than gx and gx is less than h of x, then, and if the limit of f of x and limit of h of x are equal, then limit of gx will be also the same. So that is the squeegee theorem, and this is quite useful when you prove certain inequality. So if you came from engineering departments, then probably you need to use this squeegee theorem to derive many elementary identities used in the engineering math. So this squeegee theorem is quite useful. So let me go back to the figure 7 again. So in this figure 7, the g of x is greater than f of x in this on this interval. So limit of f of x will be less than or equal to limit of gx. Now, if I compare gx with h of x, then since h of x is greater than gx, so gx is less than h of x, so limit of gx will be less than or equal to, limit of h of x. So if I combine this inequality with this one, then limit of gx will be less than limit of h of x, but it will be greater than limit of f of x. Now we have one more assumption. If the limit of f and limit of h are both L as in figure 7, then the limit of gx must be the same value L. So that is the squeegee theorem or sandwich theorem. And this is quite useful. This is simple. Okay, if you look at this figure 7, it is quite intuitive, but it is quite useful. So we have one example. So suppose that I have this product of two functions, x squared times the sine 1 over x. And I want to prove the limit of this product is 0. Okay? Now sine x, sine function, okay, is always, it is defined for any x, and the value is between -1 and 1 regardless of the value of x. So for any x value, 1 over x is between -1 and 1. Now given this, if I multiply x squared to this inequality, x squared is non-negative. So when I multiply x squared to this inequality, the direction of the inequalities are not changed. So we have these inequalities. So that means this function in the middle is greater than negative x squared but less than x squared. Now, if I take the limit, and then if I let x go to 0, the limit of x squared, x goes to 0, will be 0. And limit of negative x squared is also 0. Then by the square theorem, the limit of x squared times the sine 1 over x will be also 0. So this is one example where you can use the square theorem. Okay. So by using the square theorem, we could prove that the limit of x squared times sine 1 over x is 0. Okay. And what if I remove one power from x? If I give you just x times sine 1 over x, and then if I let this x go to 0, then what would be the limit of this? How can I, then in that case, can I use the same proof as before? Well, sine 1 over x is definitely between -1 and 1 for any x value. But when I multiply x to these inequalities, I need to be careful about the sign of x value, right? So, so if I depending on the sign of x, when x is positive, the direction of the inequalities is not changed. But if x is negative valued, then the direction of the inequalities will be changed. So if we just multiply x to this inequality, it is a little bit confusing, right? So in that case, instead of multiplying x, you can consider the absolute value of x sine 1 over x. Then that is the absolute value of x times the absolute value of sine 1 over x. Then in a similar manner as we did, the absolute value of sine 1 over x is between negative 1 and 1, or you may say 0 and 1. Now, and then if I multiply the absolute value of x to this inequality, since absolute value of x is always non-negative, x times absolute value of x times sine 1 over x is less than 0 and absolute value of x. Now, if I let x go to 0, then this limit is 0, this is 0, so the one in the middle will be 0. So from this limit of absolute value of x sine 1 over x is 0. Then how can I find the limit of x sine 1 over x? I need to use the square theorem one more time. The x sine 1 over x can be positive or negative, but it will be It cannot be greater than absolute value of x times sine 1 over x. And it cannot be smaller than negative absolute value of x sine 1 over x, right? And then if I apply the squeeze theorem, limit of negative absolute value of x sine 1 over x will be less than limit of x sine 1 over x, and that will be less than limit of absolute value of x sine 1 over x, which is 0, and that is also 0. So by the squeeze theorem, one more time, limit of x sine 1 of x will be 0. So this is one way to prove that limit of x times sine 1 of x is 0, and there may be other approaches. Okay, but anyway, if we use the squeeze theorem, then I can derive that the limit of x times sine 1 of x will be 0 as well, right? So anyway, and this is one simple example of the squeeze theorem. And if you have any questions, you can send me a message or you can email me. Now, now, please remember that moments ago, when I considered the limit of a polynomial or a rational function, so please remember that moments ago, if f of x is a polynomial or a rational function, they have some very simplifying properties, which was that limit of f of x as x approaches a equals the value of this polynomial or rational function at a. So if in case of this polynomial or rational function, it satisfies this property. Now this property is very useful and powerful, right? Without this property, if I want to evaluate, if I want to find the limit of a function, I need to apply the definition of the limit. And I need to evaluate, I need to find the values of f at many points, and then I need to identify the trend of the function. Okay? But but if this polynomial and rational function has this nice property, so if I want to find the limit of the function, we can just plug in that value into the polynomial or rational function, and we can easily identify the limit. So we are interested in this property. So we want to find certain function satisfying this property. So we want to give the name for such a situation. So we say a function f is continuous at point A if that property satisfied by the polynomial or rational function is also satisfied for this function f. So function f is said to be continuous at a point at some number a if the limit of f of x equals f of a. Now, in this expression, limit of f of x equals f of a, this implies many things. First of all, the left hand side, the limit of this equality implies, okay, this equality implies, first of all, the limit of f of x as x approaches a exists, so that the value on the left hand side is well defined. So to have a meaningful value on the left hand side, the limit of f of x as x approaches a must exist. And secondly, we must have a counterpart on the right hand side. That means previously, when I consider the limit of f of x as x approaches a, I didn't care about the value of the function f at a, right? The value of the function may be different from the limited value, or sometimes the function may not be defined at a point a. But to have this f of a on the right hand side, this function f must be defined at a. So f of a exists. In other words, f of x is defined at a. And then if the value on the right hand side exists and the value on the even the value on the left and the value on the right both exist, then they must be the same. They must be equal. Okay? The value on the left and the value on the right must be equal. So this condition implies three things. First of all, the expression on the left must be well defined. Okay, it must be a certain number, certain value. And the right hand side must be well defined. In other words, the function must be defined at a. And then thirdly, these two sides must be equal. Okay. Oh, and one thing. Okay. Please check the Zoom ID and screen number, screen name. The Please change the display name to your student ID number, not your actual name. Some students are using their actual name combined with the student ID number, but please remove your name. I just need just the ID number only. Okay, so please read the instruction, okay, on the guideline on the LMS website. So if you are new to this class, please check the guideline on the LMS website and please change your display name to your student ID number. If you use your name, it is very difficult to check the attendance. So please change your display name with your student ID number. Still, some students are using the actual names. Please do not use those. Okay, so please use the student ID number when you log into this class. Anyway, so we say a function is continuous at a number a if that equality holds. Okay, so as I said, the value on the right, f of a, must be well defined, and the left expression, the limit of x, must exist, and thirdly, these two values must be equal. If this holds, then we say the function is continuous at a. Otherwise, if the function is not continuous, so when I say otherwise, then that means either one is, not either, okay? If the condition 1 is violated, or condition 2 is violated, or condition 3 is violated, then we say the function is not continuous, or simply we say the function is discontinuous at the given point. Okay, so when I say the function is discontinuous at certain point A, then that means at least one of three conditions for continuity, these three, is not satisfied. So as an example, in this figure, okay, my function is not defined at 1. So that means my function is not continuous at point 1. At 5, my function is defined. So it has this value, but that value of the function is different from the limit of the function at A, because all the nearby neighbor points of 5 will have the function values close to this one, this value, but at point 5 the function value itself is different. So the left hand side and right hand side are different. So the function is not continuous at 5. At 3, the left hand limit and right hand limit of the function are different. So the function does not have the limit. So the expression on the left of the continuity does not exist. That means this function in figure 2 is not continuous at 3 either. So this function is not continuous at 1, 3, and 5. At all other points, the function seems to be continuous. So when I look at the function, the f in A, I have x squared minus x minus 2. The numerator is a polynomial. Denominator is another polynomial, x minus 2. Okay, but so f of x is a rational function. So rational function is continuous as long as the polynomial in the denominator is well defined. And the polynomial in the denominator is x minus 2, and that is well defined as long as x minus 2 is not 0. So in other words, f of x will be continuous, okay, as long as x minus 2 in the denominator is not 0. So in other words, this function will be continuous at all points except 2. At 2, the denominator is 0, so that the function is not defined, it's not continuous. In B, we separated the x values. Okay, so when x is different from 2, we have this rational function. But if x is 2, I assigned the value 1. Then, okay, then when x is not 2, then my f is a rational function and the rational function is well defined. When x is 2, function is also defined. Then is my f in B continuous? So in B, limit of f of x as x approaches 2 is defined. F of 2 is defined. The question is, do they have the same values? Well, if I plug in now, what is the limit of x squared minus x minus 2 over x minus 2 as x approaches 2? So what is the limit of x squared minus x minus 2 over x minus 2 as x approaches 2? Well, if I factorize the numerator, x squared minus x minus 2 can be factored into a product of x plus 1 times x minus 2. Now, as x approaches 2, so as x approaches 2, then that means x will be very close to 2, but so this expression means x can be as close as we want, but not not 2, as close to 2 as we want, but it cannot be the value 2. So that means x minus 2 is not 0. So this part means x minus 2 is not 0 when I consider this a limit. So x minus 2 can be cancelled when I consider this a limit. Then we have limit of x plus 1 as x minus x approaches 2. Now at this point, x plus 1 is a polynomial. And if I consider this a limit of a polynomial, you can plug in the value into the polynomial directly. So you get 2 plus 1, which is 3. So that will be the limit of this function f as x approaches 2. So the limit value of f of x is, that is a 3, but the value of the function f at 2 is 1. So even though this left hand side and right hand side are well defined, they are different. So this function f in B is also discontinuous. This function is discontinuous at 2. Okay. Now, when you look at C, I have 1 over x squared function when x is non-zero. And when x is 0, f of x has the value 1. So when I consider the limit of 1 over x squared as x approaches 0, is it well defined? What is the limit of this? We considered this limit moments ago in the previous slide. That was infinity. And is it the same as the value of the function at 0? No. So this function f in C is not continuous at 0. So this function is not continuous at 0. Now let us look at the function in D. So we have this symbol, okay, of x. What does that mean? So that represents, we use this symbol to represent the largest integer less than or equal to x. Okay, so that is the meaning of this symbol. So let me use some example. So for example, if I use this notation with say 2.5, then the largest integer less than or, oops, just a second. Okay, then the largest integer less than or equal to 2.5 will be 2. Then how about 2.9. The largest integer less than or equal to 2.9 will be also 2. Then how about 2? Then the largest integer less than or equal to 2, it will be 2. But if I change this to 3, then it will be 3. So that means for all the real numbers between 2 and 3 except 3, for all values between 2 and 3 are mapped to the value 2. And then use starting from 3, 3 is mapped to 3, and then up to number 4, all the values between 3 and 4 will be mapped to 3. And this pattern will be repeated. And of course, between 1 and 2, all the values will be mapped to 1. And between 0 and 1, the values will be mapped to 0. So this will be the graph of this function. As you can see, say at 1, the function does not have the limit at 1 because the left hand limit and the right hand limit are different. At 2, the function is not continuous because the left hand limit and the right hand limit are different. So from this, we can check the following. This function is continuous for when x is not an integer values. Okay? But this function is discontinuous so at integer value the x, the function is discontinuous. But for all other points, the function is continuous. Right? So for example, if I consider say 3.5, if I consider very small neighborhood of 3.5, I mean 3 point, then the limit of the function and the value at 3.5, I mean the limit of the function as x approaches 3.5 and the value of the function at 3.5, they are equal. But at all integer valued x points, the function is discontinuous. Yeah, I already explained this one. And okay, now, okay, so let me draw the graph of this. So as I said, this is the graph of the all 4 functions considered in the example. And as I said, as your x approaches 2 in example 1, the function value approaches 3. But the function is not defined at 2, so the function f in A is not continuous. And in case of B, function is defined at 2, but it has the value 1, not 3. So the trend there 2 is different from the value of the function at 2. Okay, so the limit of f of x as x approaches 2 represents the trend of the function values near 2, and the value at 2, if they are the same, then we say the function is continuous at the point, but in this case they are different. Okay, now when I look at this point A, when I look at the graph in A or B, what if I change the value of the function at 2? I mean, if I, so here in in A, we have x minus 2, x squared minus x minus 2. So that is f of x in A. And so 2 is excluded from the domain of the function f. But in B, we have the value at 2, but the value is different from our expectation. So in A and B, the functions are not continuous. They are discontinuous at 2. But what if I introduce a new function, say f tilde, such that it has the value when x is not 2, but when x is 2, if I assign the value 3, then this f tilde will be continuous, right? In other words, the point I want to tell you is that even though A and B are discontinuous, okay, I can eliminate this discontinuity if I assign this specific value, then I can eliminate this discontinuity, right? So because of this, the discontinuity in A or B are called removable discontinuity. Means I can fix this discontinuity by assigning an appropriate value at 2, then the function will become continuous. So I can fix this discontinuity. So that's why the discontinuity in A and B are called removable discontinuity. Now, in case of C, I cannot fix this because at 0, I mean, this is, we are looking at the graph of 1 over x squared. At this point, I assigned the value 1 as the value of the function at 0, but no matter what value you assign, the function will be always discontinuous because the function values are approaching infinite at 0. So in that case, I cannot fix this because the function values are increasing without bound. So in that case, we call such a discontinuity as infinite discontinuity. In case of D, we have slightly different situation. The function values are all finite, okay? But I cannot fix this either, right? And because we have jump. Actually, we have jump here at these integer values. And in that case, I cannot fix this. And no matter what you assign to the values at those integer values, your functions will be still discontinuous. But anyway, at each point of discontinuity, we have a jump from the left-hand limit and the right-hand limit. So such discontinuities will be called jump discontinuity. And this one will happen quite often in many engineering fields, right? But anyway, let's call it a day here and see you see you next week. Okay. And please read the materials. And if you have any questions, please email me. especially if you are new to this classroom, please email me if you have any questions. Okay, see you on Monday.